So thank you for the invitation. So the work that will be presented is mostly the work of the PhD of Odeline, and since she is in the same room as I am, she will actually do the presentation.
Okay.
I will give her the floor.
Okay, great. So welcome, Odeline, then.
Hello, everyone. So I'm going to try to share my screen.
Yes.
Okay.
There was a last question from Philip, but I think we can maybe discuss that afterwards. We have a little bit of time after the last talk. Okay, so we see your screen.
Great. And can you hear me correctly?
Yes.
Great. So this is the title of this presentation, which is Triggering New Deformation Mechanism in TA64 by Heat Treatments, a step forward into the improvement of the ductility and the work hardening of 3D printing parts. And on that subject, we were three main people. So Stéphane Godet, you know him, and also Frédéric Prima, because I'm doing a PhD under a co-supervision, so both at ULB, but also at Chimie Paris. Okay. So I tried to change the slides. Okay, great. So at first I will start with a tiny introduction with very general notions. I'm sure you know all of it, and a lot of them were introduced in the presentation this morning, but just to be sure that we have all this notion in mind. So we work on titanium lows, and more especially on TA64. And you know that we use this kind of material generally because they have an excellent strength to density ratio. But the main problem of such a material is the fact that we have a very low work hardening, and the work hardening is qualitatively defined as the capacity of your material to progressively harden during plastic deformation. And quantitatively, we describe this value as being the difference between the ultimate tensile strength and the yield strength. And we computed the work hardening on the classical alpha plus beta TA64 microstructure. And as you can see, we had 150 megapascal of work hardening, which is quite low. And the fact that we have a low work hardening is often associated to a low uniform strain, a high sensitivity to strain localization. Often you don't have a lot of absorption ability. And that's why we want to try to improve the work hardening to try to improve that other properties. And it's even more important in the context of 3D printing, because you all know that we can have in such a 3D printing, in a 3D printing parts, we can have defects that are inherent to the process. And if you have a material that is very sensitive to strain localization, it's going to cause the early fracture of your parts, and we want to avoid that. And that's why we want to try also to improve that work hardening, to try to give a bit more of a damage tolerance of TA64. But we are quite restricted because you know that at the outcome of the process in 3D printing, we have the final shape of the part, so we cannot deform the piece to improve the mechanical properties. So we have to find something else. So to do so, to improve the work hardening, we based the work on a previous study, which developed a microstructure which is called dual phase, because it is composed of two phases, alpha and alpha prime, as you can see on this micrograph, which is with the phase which is the light one is the martensite, and the dark one is the alpha phase. And as you can see on these two true tensile curves, the dual phase microstructures allows to improve the work hardening. We almost doubled, we more than doubled the work hardening. So it's quite interesting. And it's quite easy to have such a microstructure because you just have to heat your material during 2 hours in the alpha plus beta field, and then to do a quench to transform the high temperature beta phase into martensite. In such a microstructure, we could explain mechanical behavior thanks to DIC measurements, so digital image correlation, as you know, during a tensile test. And thanks to that, we could see the deformation of each phases. And it is in fact the martensite that tends to deform to larger extent than the alpha phase. So it creates a great mechanical contrast between the ductile martensite and the less ductile alpha. And thanks to that, you progressively harden your material. Another way to describe it is the fact that the martensite wants to deform, but not the alpha phase. It progressively creates mechanical incompatibilities at the interfaces, and we can see it on the map of the deformation that you have on the right. Because we have mechanical incompatibilities at the interfaces, it's progressively harden your material and you improve the work hardening. So that was about the global description of the mechanical behavior of the dual phase microstructure. But at this stage of the analysis, we considered the martensite as an average metal, and we didn't consider at all the complexity of such a phase, which is in fact very heterogeneous, because that's a phase which is composed of a lot of interfaces that takes place between very thin and acicular plates. So one of the first goals of this study is to zoom on this phase to try to find the role of the interfaces of the martensite, and try to find, we're quite sure that to explain the role of the martensite, we have a collective role of all the stuff that we can find in the martensite. So we want to try to highlight that. And the first surprising observation was the fact that when you have martensite in TA64, but when you quench not from alpha plus beta field, but from just the beta field, so at higher temperature, the martensite is referred to be very hard and brittle. And here it's not the case at all, because in our case, in the dual phase microstructure, the martensite is in fact the ductile phase. This is why we want to go deeper into the comprehension of the martensite, because we are sure that knowing a little bit more about this phase is going to give us some clue on how it works on the dual phase microstructure in general. So to do so, we used a strategy which is to do a crystallographic study of this martensite, because it's very useful to have some information on the interface, to take into account that we obtained such a martensite thanks to a phase transformation. And in case you wondered, the reasons why we don't have exactly the same microstructure for the dual phase in that slide compared to the previous one, it's just because you can see that the study, it's a bit different. It's not about the process of 3D printing, because we have our part and then we try to do a heat treatment to improve the properties. So it's more about the microstructure. And to avoid the problem that we can have in 3D printing, such as the difference in composition that we have with different batch, and also the fact that we can have some defects, we choose to do this analysis on forged material, but the application remains 3D printing, and we check all the rules and all the results that we have on 3D printing parts. So what about this martensite? The first thing that we can say, thanks to a TEM bright field, is the fact that we have a quite typical martensite composed of stacking faults and also transformation twins. And a first thing that we can say that characterize such a martensite is the fact we have quite parallel plates of martensite, which is not always the case in the martensite. Then if we take a look at this martensite, thanks to an EBAC map, you can also find the fact that the martensite organized itself into a parallel way. But we can also see that there is only two mesoorientation taking place between the plates of martensite. And it was saying that in fact we have a selection of misorientation, because usually in the martensite of TA64 you can find 5 different misorientation, and here we just have 2 of them. And we also have one which is favored, the one at 63 degrees, because the fraction of this one is about 0.4 compared to 0.14 for the one at 60. Then, as I said, we did like a complete crystallographic study. I will not go into details, but what we have to know is that the martensite is obtained through a phase transformation. So at high temperature, you have the beta phase, and you quench the beta phase to create the martensite. The beta phase and the martensite are linked by an orientation relationship, which is called the Berger's orientation relationship. You can find the illustration of such a orientation relationship in the middle. And thanks to that, we can say that from one variant of beta, you can create 12 different variants of martensite that have the same probability to be produced. And you have these 12 possibilities on the table on the right. For the rest of the study, we put a number to each variant from 1 to 12 because we want to track the variant experimentally. So how to do so? So at first you have to start with the orientation of the martensite. Then, because we know about the Berger's orientation relationship, we can recreate the orientation of the high temperature beta phase. It's what you have on the left. And because now we have both the orientation of the martensite and of the high temperature beta phase, we can say, okay, in that particular martensite variant, I have the variant number, I don't know, for example, here, variant number 1. And it's what we did on the right. We did it for all the martensite variant. We put a number on them to reconstruct the map of the variant. Okay, so that was for the construction of the maps. But now, what about the results we have? So theoretically, we said that from one variant of beta, you can create 12 variants of martensite that have the same probability to be produced. But experimentally is not what happened at all, because as you can see, each parent beta grain mostly transform into 4 different groups of 3 variants. So for example, the parent beta grain, which is marked by an arrow, is mostly transformed into group 2, composed of variant number 1, 5, and 8. Then another interesting information is the fact that the misorientation of 63 degrees, the one which is favored, take place between the variant of the same group, whereas the one at 60 degrees take place between 2 different groups. So we don't have a random organization of such a martensite. It's organized into 4 groups of 3 variants, and the groups are characterized by the misorientation at 63 degrees. But now we need to understand the reasons why we have such organization. So to try to understand, we tried to compute a value which is called the shape strain of a variant, as you can see here. To do so, we used a theory which is called the phenomenological theory of the martensite crystallography, called PTMC, because it permits to compute some experimental data that can be checked experimentally, some data that can be checked experimentally, such as the shape strain. What is the shape strain? It's just the fact from beta you want to create a variant of martensite, and it's going to induce an amount of deformation. The shape strain is just the quantification of that deformation. And you can see that it depends on different crystallographic data, such as the habit plane, the direction of the shape strain, and the magnitude of the shape strain. Now, if we compute that value, for example, for the 3 variant of group number 3, meaning the variant number 4, 7, and 11, you can see that on average, the shape strain matrix of the variant of the same group gives a result which is quite close to the unit matrix, saying that there is a compensation of their individual shape strain to minimize the transformation strain. In other words, if we have this particular variant next to each other, it's because they are going to compensate their deformation linked to their creation. So they're going to try to minimize the energy which is linked to the transformation, to the phase transformation. And when you have such organization of martensites, we talked about self-accommodating martensites. And in our case, we have 4 self-accommodating groups composed of 3 variants, and they were characterized once again by the misorientation at 63. So, okay, at this stage we know about the groups and the misorientation, but we don't really know the nature of the interface that we have between 2 a variant of the same group. So to try to figure out, we performed a TEM analysis, and that's the results. So on the left, you can find a bright field image of 2 plates of a same self-accommodating group here. And we took a diffraction pattern at the interface between these 2 plates. And as you can see, the interface is not a random one, because the variant of the same group are in fact twin related on a twinning plane, which is the 1, 3, -4, 1. And it was a quite interesting result, because to our knowledge, this twinning plane was already predicted theoretically, but not experimentally assessed yet. So that was about the description of the martensite in the dual phase microstructure before deformation. So we don't have a random organization. We have a self-accommodated microstructure with 4 different self-accommodating groups composed of 3 variants. They are the variant of the same group or twin related, and they were characterized by the misorientation at 63 degrees. So now we have the complete description of the martensite before deformation. So the idea is to have a look at the martensite after deformation to see and to try to understand its mechanical behavior. So to do so, we did exactly the same thing, starting with an EBSD map of the martensite after deformation. The first thing that we can say is the fact that the 2 misorientation, the one at 63 degrees and the one at 60, still remains after deformation. But the fraction of the one at 63 degrees has greatly decreased, because you can see we have a fraction of 0.05 instead of 0.4 before deformation. And by contrast, the one at 60 degrees remains in a quite equal proportion. But to have a clearer view of what we have after deformation, we also did the reconstruction of the variants, and you have here the results. So it's easy to say that the microstructure has significantly changed, and more especially, we have 2 extreme cases. The first one in grain 1, 2, 3, 4, where a single variant remains after deformation. And by contrast, in grain 5, we can see that all the variants remains in a quite equal proportion. So, based on the fact we saw that the fraction of the misorientation at 63 degrees has greatly decreased under the effect of deformation, and that in some grains we have just 1 variant that remains after deformation, we can see that the interfaces related to the misorientation at 63 degrees is in fact mobile under the effects of deformation. And when you have such a deformation mechanism, we talk about reorientation. And it was quite surprising to find it, because it's usually a prerogative of shape memories allowed martensites and not the martensites in TE64. But to be completely sure that we have reorientation, we wanted to compute a value, which is called the interaction energy, because in shape memories laws, generally, when you have a martensite that can induce reorientation, the variant that can grow at the expense of the others are the ones that maximize the value. Yeah, I don't know if we was very clear about it. When you have reorientation, is the fact that you have several variants, and 1 variant can grow at the expense of the others under the effect of deformation. And thanks to the if you compute the interaction energy, the variant that maximize this value should be the one that grow at the expense of the others. So we want to check if it works in our case, if it's the case. And if it works, it can be also very useful to try to predict the reorientation, because you can compute this value on the martensite before deformation. And if you know the direction of your stress, you can say, okay, I know this variant will be the one that will grow under the effect of deformation. And as you can see, this value depends on the microscopic stress and also on the shape strain, a value which was already computed. And what is this physical signification of the interaction energy. It's just the energy which is consumed by a variant in the tensile direction. So this is expressed as an energy, but you can also see it as a deformation. So it's also the deformation that can be given by a variant in the tensile direction. So we try to compute this value on the experimental case. For the two extreme cases, the first one of a complete reorientation and a second one of no reorientation. So in the first one, we can see that after deformation, we just, the variant that remains, it's variant number 9. And because we know that before deformation, we had a self-accommodating group that were complete, we should have before deformation also variant number 12 and variant number 6, because the variant number 9 is in the group number 4. So before deformation, we had variant number 12, variant number 6, and variant number 9. And after deformation, we just have variant number 9. And if we take a look at the interaction energy, it seems to be true, because the variant that grew at the expense of the others is the one that has the highest interaction energy. And we can go further. We can say that it seems like to have a complete reorientation in a parent beta grain, we need to have one variant that has a positive value of the interaction energy and two variants that has negative value of the interaction energy. And the one that is favored, that means having a positive value of the interaction energy, will grow at the expense of the one that are in favored. By contrast, in grain number 5, we had in that case two groups, two self-accommodating groups, group number 2 and group number 4. And we can see that, for example, in group number 2, we have variant number 1, 8, and 5. And we have two variants that have a positive value of the interaction energy, meaning that are both favored. So they both want to grow at the expense of the others. So we think that in that case, it will compensate. No one will grow at the expense of the others, but they can grow at the expense of variant number 5, because variant number 5 has a negative value of the interaction energy. So thanks to that, we can build some criterion, which is the general one is to have orientation between two variants. You just need one favored and one unfavored, and the one which is favored will grow at the expense of the others. But to have a more specific criterion, which is at the scale of a self-accommodating group, you need to have one variant which is favored and two that are unfavored. And that's the only case where you can find a complete reorientation at the scale of a self-accommodating group. Based on that last criterion, we did a theoretical study, and that's the result. So I'm going to explain to you the steps of this theoretical study. We took 5,000 random variants of parent beta grains. So we took different orientation of the beta grains. From each orientation, we computed the 12 variants that can be created from this beta. And we sorted them by self-accommodating groups. And on each self-accommodating groups, we tried to compute the interaction energy to see if we are in the case or not of one variant favored and two unfavored. And we counted the number of groups that respect this criterion. And as a result, we have from 0 to 3 groups that respect this criterion. And experimentally, in practice, what is the consequence? The consequence is that we have a strong link between the orientation of the parent beta grain, so the texture of the parent beta grain, and the fact you can induce or not reorientation. So for example, if you have a texture close to 100, you cannot create self-accommodating groups that can induce a complete reorientation. And it was experimentally the case, because in grain 5 we couldn't see some complete reorientation, but it was just because it wasn't possible. By contrast, if you have a texture which is close to 111, you have a high probability to create self-accommodating groups that will respect the criterion to induce a complete reorientation. And close to 101, we were in a case of grain 1. We have a quite high probability to induce complete reorientation, and that happened. So, okay, we know now that the occurrence of reorientation depends on the texture of the beta grains. And we know that close to 111, we have the highest probability to induce reorientation, but we also have to take into account another data, which is the value of the interaction energy. Because even if we have the highest probability to induce reorientation close to 111, we have in fact a very low value of the interaction energy. And if we have a low interaction energy, it's, as I said, your variant will not give a lot of energy in the tensile direction. So it will not give a lot of deformation in the tensile direction. So we can see it a bit like the efficiency of the reorientation. So you have a high probability to have reorientation, but it will not be very efficient. By contrast, next to 101, you have both a high probability to induce reorientation and also a good efficiency. So we think that it is the best compromise to have reorientation. As I said, you can see this interaction energy. You can express this as an energy, but also as a deformation. So it's what we did on this on that IPF. And you can see that at the maximum, we can reach 9% of deformation. And if we compare that value of the one that are given in the literature in a classical shape memory allows titanium nobium, at the maximum, we can find 4.4% of deformation. So in fact, in our martensite, the deformation that can be reached thanks to reorientation are quite high. So based on that, we think that reorientation can at least in part explain the ductility that we found in the martensite to try to explain. So we were at the scale of the martensite, but now we go back to the scale of alpha prime and alpha. And the surprising observation was the fact we had a lot of ductility in the martensite, and we think that reorientation can at least partly explain that this martensite is ductile. But we have to keep in mind that it's quite complicated because we know, I didn't show it here, but we know that reorientation starts at the beginning of plastic deformation, but it's in the same region where the dislocation glide will start. And we also know that depends on the texture of the parent beta phase, all the martensite will not bring reorientation. So we have all of that in mind, and it works all together. We also have the mechanical contrast between alpha and alpha prime. And we think that because all of that, the reorientation will be harder and harder to induce. And maybe we also have some work hardening thanks to that effect. So now what we have to do is to try to go deeper into the comprehension of what is the real impact of reorientation on this microstructure, which is quite complicated because we have a lot of scales, a lot of different phases that are in interaction. Sorry. So that's the following steps. And to conclude on this martensite, after deformation, I can say that we could find some reorientation on the martensite of TA64. We can also say that we use the interaction energy to rationalize the reorientation, but we can also use it to predict the reorientation. And we think that reorientation can explain, at least in part, the ductility of such a martensite. And if you're interested in that work, you can find a bit more of it in the paper, which was written in the paper ACTA. So thank you for your attention, and do not hesitate if you have some questions.
Thank you very much. So it's open to discussion. I don't know if I don't see at the moment questions, so as usual, I will maybe start. So I was wondering, I mean, if you could, making the link with the previous presentation by Eric, couldn't you do some kind of in situ test where you use the IC and see how much of each phase, the martensite, the alpha and the alpha prime deform under loading? That would give an idea maybe of how much you accommodate in the martensite compared to the matrix. I mean, to the alpha.
We already have the information about, we know that the martensite deform at larger extent, but we also did the IC also to try to, okay, in the grains that can induce reorientation, because I can predict that. Do I have more deformation that in the other grains or not? But we have to look at the results. We did it, the experimental parts, it's done, but we have to.
Okay, so you can make the link between the extent of deformation in the martensite and the amount of reorientation.
Yes, exactly.
Yeah, okay, I see. Yes, that would be interesting indeed. How can you explain why it's never been observed before? Because it's a material which is quite well known, Ti-6-4. So do you know why no one has noticed that before?
Yeah, I don't have the right answer, but I think no one likes it because it's usually referred to be hard and brittle, and it was quite surprising at first to find out that it's the ductile phase in our case. But I don't know why. It's a question that I was asking also.
And also maybe a last question: when you're finished reorienting, you have only one variant left. Then you expect then the ductility is gone then in that phase.
Yes, and we have, in fact, we have like, if we look at the Schmidt factor, we have like a very precise scenario because we have a Schmidt factor which is very low for the basal plane and very high for the prismatic plane. So thanks to that, I was like, okay, maybe I can reorient and to have like very hard grains, for example. But it's not so clear because the CRSS of both basal and prismatic are quite the same in the Ti-6-4, in the martensite of Ti-6-4. So it's hard to say, but we think that in fact the ductility is decreasing.
Yeah, I guess because, yeah. Okay, I don't see any other questions. No, this is very particular. Actually, this is a talk not so much related to additive manufacturing, is it?
Yes, I don't know if I was clear about it because the application is 3D printing because we want to try to optimize such a microstructure to have work hardening and then try to use this work hardening to improve the damage tolerance of the microstructure. But you're right, we're not touching at the process, we're just doing the post-process part.
Okay, yeah, I see. But then in additive manufacturing, I mean, you also have internal stresses that are built during the transformation, right? The beta to alpha transformation. So don't you have an influence of those stresses on the variant selection during the process? I don't mean during the post-processing.
In fact, maybe it has an influence, but not on. I don't think on that part because we looked at the martensite of the deformation on 3D printing, and we could also find some orientation. But in fact, you have some difference because the size of the martensite is not exactly the same. The morphology of both of the dual phase microstructure in general, it's a bit changing. And also you don't have the same texture, and we saw that the texture have an influence on this reorientation. But it's more about it than the constraint. It doesn't seem like very difficult for the interface to move. And we had the opportunity to work with someone that worked on AB initio computation, and he found out that it's very easy to move the interface, which is the 1,3 - 4,1. So we think that is not a problem, even if you have some constraint in the 3D printing parts.
But so even if you're fully alpha prime, you could move still the boundaries between the variants.
Depends. You have to check the chemical composition because, for example, in our case, we did try some other temperature heat treatment, and when you go to higher temperature, your martensite will be with more aluminum, and we think that it's gonna, when you are, or in this case, we cannot see reorientation anymore. So we think that because of the chemical composition, you have this ability to induce reorientation or not.
Oh, I see. There is a question in the chat asking you to give more information about exactly that, about the post-heat treatment that you use.
Okay, on 3D printing parts or on forged material? Because we did both.
I guess Adrian needs to say, you can talk if you want. 3D printing, he says. Okay,
so on 3D printing, it's we did try on HIP material, TA64, but the process was EBM and not SLM. So EBM parts with a Windman-Staten microstructure, then HIP treatment, and then the dual phase heat treatment, which is quite simple, just 2 hours at 920 degrees, followed by the water quench, and that's it.
And the duration?
Of the heat treatment, 2 hours.
Okay, all right, I guess that's what he wanted. All right, maybe a last question from Manas.
Yes, thank you, Odeline. So based on whatever knowledge you gained from your post-treatment studies on 3D printed materials, could you envisage something that you could do in process? So instead of doing the post-processing, could you treat the material while it's being built so that you, for instance, you stop the process after building a certain number of layers and you heat treat it and then you continue building? Could that be done? Could it be controlled that way?
What could be interesting is to try to have the finest microstructure possible, because when you have very tiny martensites, you improve your change to have one self-accommodating group in 1 parent beta grains, because when you change the size of the parent beta grain, you will have not one but several self-accommodating groups, and between them they cannot induce reorientation. So it will be better if you have just one. So maybe we can adjust the process on that point, but I think that's it.
Okay, I have another question on the chat from Charlotte, congratulating you on your work, and then asking the range of temperatures for your heat treatment, which would allow you to see these reorientations.
Okay, that's a good one, because we could see, so from 800 and 920 degrees, we could see reorientation, but above that, the reorientation is gone. So we think, we don't know at this stage if it's linked to the chemistry or the size of the martensite. We think it's both. It's more a problem of chemistry, because we could find some other alloys that has very big martensite lath and that can induce reorientation without any problems. So we think that it's more a question of chemistry. And it's one of the criterion that helps to see it is the MO equivalent, because when you have a MO equivalent that is negative, it seems like it's going to, you can induce reorientation when you are in that case. So you have to check the chemical composition, but we are working on that topic.
Yeah, that's ongoing work. Okay, thank you very much for this nice presentation, nice work. I think we can stop now.